Okay. And kind of reset itself a little bit, but not much. I think we're good there. Okay. Um. A line in three-dimensional space. Okay. If I want a line from here to the upper corner of the room over there. If I have a coordinate system, let's just say that that lower corner over there is the origin. So we're ahead about 10 feet and over about 9 feet. And up, that point was up about 5 feet. So that point might be 9, 10, 5. Make sense? Can you visualize that? And back corner there might be 31, 28, 9. Yeah, seems about 9 feet. Okay. So let's just think, okay, we want to do a line from the point. Nine, 10, 5, I think I said 31, 29, 9. Okay. Well, any point on the line has to lie on a multiple of the vector that goes from here to there. If you think about it, what's half of the vector that goes from here to there? Still in the same direction, isn't it? What's -6 times that vector? Well, it's in that direction, down through the floor and into the subsoil. Okay? Makes sense? So. Vector from the first point to the second is 22i J and K plus 19j plus 4k. All that big. Okay. Now I can draw kind of a diagram here. Direction they send is unfortunate, but let's say go 10, 9, 5, let's do that. Then we have this vector back toward the corner. Not very straight, but you get the idea. Okay. I'm sure that's drawn in the proper perspective for this room or the numbers. But we could plot 31. See, that's 10. Well, let's just see where 10 is. No, 5, 5, 10 here, 9 here. So we see projection line down into the XY plane and over here to where X is 10, over here to where Y is 9, and up here to where C is. It makes certain sense. Yeah, 10 here, 9 here, 5 here. Give you this point. And you can even, complete a rectangular solid through these points to help make sense of them, right? And you can say, okay, well, there's a vector that goes from the origin to this point, and then a vector here that goes along the line. Then the line continues. Okay, here's the line. Has to go through this point, has to be parallel to this vector. Be more parallel if that vector is a little straighter, Okay. So here's the line. Okay. Any point on the line Here's a point X, Y, Z. Okay. A vector from here to X, Y, Z has to be parallel to this vector, right? So what's this vector? Well, this vector is X minus 10I plus Y minus 9J plus Z minus 5. Okay, everybody with me? Because how far you have to go in the X direction to get from here to there? Well, you're already at X equals 10, you gotta go out to X, so you gotta go X minus 10 units, right? Okay. And you're already at Y equals 9, so you gotta go Y minus 9 additional units. You're already at Z equals 5, okay? So you gotta go Z minus 5 units. There's your vector. Make sense? Need a second to process it? Go ahead and process it. Depending on whether you can visualize it or not, you have to accept this. If I add these up, 10I plus X minus 10I is X. Nine J plus Y minus 9J is just YJ. 5K plus what is Z minus 5K is just ZK, right? So my vector from the origin out to this point, and again, the perspective here was not a good one. I should have gone to that corner there. We'd have a better picture. But you know, I can cut from here to here. This purple vector is xi plus yj plus zk. All right. It differs from this vector by this vector, because this vector plus this vector equals this vector. Okay. This plus this equals that. So this has to be this minus that. A plus B equals C. So B equals C minus A. Okay. And the algebra for the vectors just mimics the algebra of real numbers at this point. Now there are differences. And you're going to get plenty of differences in linear algebra and here. If you're taking linear algebra, if you took it. Okay. So right there it is. Don't need to say anymore. I'll do something a little different than that. So was gonna say plus the V vector, because the vector from the origin out to this point is this one, right? Um, and I'm gonna then say where this AI plus BJ plus CK vector is some multiple of V. That makes sense? This has to be a multiple of V. Yeah, I can think of a different way I could have written that, but that should be something you can see. Um, stop there for a minute and talk about the dot product. You all seen dot product in linear algebra yet? So everybody knows what dot product is. Okay, so I don't have to develop it. Okay, but A1I plus A2J plus A3K. Well, let's say left. W equals B1I plus B2J plus B3K. Also, B dot W is the magnitude of V times the magnitude of W times the cosine of theta being the angle between. Everybody familiar with all that? Have you seen that? Understand that? Okay. Meaning that the angle between these vectors is the inverse cosine of this divided by this. That makes sense? Have you seen that? You're familiar with that? Okay, so I don't need to say too much about it. So this means you can find the angle between any two vectors in space. And actually, you can extend this to any number of dimensions, and you will do that in linear algebra. In this course, we'll stick to 3 dimensions. And in advanced physics, you go to many dimensions. But for this course, we'll stick with 3, because the mathematics gets weird. Some of the mathematics gets weird if you don't have linearity. As long as everything's linear, there's nothing weird. It's just hard to visualize. You can't really visualize it. As soon as things start curving and doing weird stuff, that gets all out of kilter. So we're going to learn it in 3 dimensions. And then if you ever need to extend it, you'll have a basis. Kind of tough stuff. Okay, there's your dot product. Okay, I want to keep myself on track. Let me check my note for topics. Okay, so how do you, let me just, I'm gonna ask and then pause and we'll talk about it for a minute. How do you test whether two vectors are orthogonal? Okay. Okay, now, if you couple in a Euclidean space, orthogonal means the same thing as perpendicular. Okay, that means like R2 or R3, okay? Two-dimensional, three-dimensional, usual Euclidean space with Euclidean metrics and all that stuff. So clearly, if the vectors are perpendicular, theta is 90 degrees or pi over 2, okay? And a cosine is 0. So you extend the idea of perpendicularity to orthogonality. Now here in physics, if we're in 3 dimensions, orthogonal and perpendicular again mean exactly the same thing. Okay, but you get into function spaces, you know, dot product of 2 polynomials. You guys probably haven't seen it, but you do. I guess a little where dot products of functions where you integrate the product of the 2 functions to get the dot product. Okay, so I guess that extends this whole thing, and you'll see that in linear algebra. You're not going to see that in physics. You're not gonna, you know, this isn't physics, this is monodromal. You won't see it in monodromal calculus. Okay. All right. So we got the idea of orthogonality. So let me just give you a problem to do. I'll do 2 dimensions, but 3 dimensions is equally easy. Two vectors with an unknown here. V dot W is 0, so what's the value of A? Okay, at least one person came up with a solution to 6. Let's see how you get it. B minus W equals 2A minus 12, right? B, that's A minus, B dot W is 2A minus 12. And that has to equal 0. Because these things are orthogonal. We solve that. We get it equals 6. Okay. Now, if you're in 3 dimensions, could I add a BK with some multiple of J or multiple K up here? Could I solve it if I did that? I get 2 simultaneous equations. Well, would I get 2 simultaneous equations? I get 1 equation with A and B. I'd have 2 unknowns, so I might be out of luck. And well, you can sort that sort of thing out if that arises in the problem set. There's pretty good problems in this problem set. Okay, some of them make you think a little. Okay, so we're moving through this pretty fast, but I want to move through it fast when we can, so we can slow down when we need to. Oh, have a great day. Okay. What direction does that line make with each axis? Well, it depends on where it projects down to the XY plane, doesn't it? Okay. In other words, if it projects down to the XY plane here, it's much different than if it projects down to the XY plane here. Okay. You can't tell. It's a 2-dimensional picture, and you can't estimate the angles in a 2-dimensional picture. But if we say this is D, equals AI plus BJ plus CK. It makes some angle with the x-axis, makes some other angle with the y-axis, and it makes another angle with the z-axis. We call these angles alpha, theta, and gamma. That's a pretty standard notation. You see it just about everywhere when this is discussed. Okay. Matter of fact, I can never remember seeing a different notation for these three angles. Okay, well, how do you determine the angle alpha if you know the components of the vector? Okay, I don't remember if I posed the question when we were on camera or not, but I asked, okay, alpha is the angle between two vectors. One of the vectors being v, and what's the other vector? Well, what you know about the other vector is it lies along the x-axis, right? Because you looking at the angle between this vector and the x-axis, you just pick any vector in the x-axis and find the angle. Okay, it'd be alpha. Be the inverse cosine of dot product of that with whatever vector along the x-axis you might want to choose. Okay, divided by the product of the two magnitudes. Well, the angle, simplest angle to choose might as well choose the simplest one. Although if you wanted to do 7.832956 times I, which is one of my favorite vectors, you could. Any vector, any multiple of I would do it, right? I could even do simple C times, or no, you don't want to use C because we've already used it, but D times I. Okay. But I is sufficient, so why complicate it with a coefficient? Used up too much room, so the cosine alpha is part of this, right? Understand that? Okay, well, give me the expression for the cosine of alpha in terms of, oh crap, I mean chunks, A, B, and C, okay? A nice piece of chalk broken into three pieces are all useless. I'll put you in the spot to see. If you got it right or not, I think you'll recognize it, okay? The inverse cosine of what? V dot I, which is A, over product of the magnitudes. Magnitude of I is just one, magnitude of V is, of course, officially the magnitude of V is the square root of V dot V, right? That makes sense? Okay. And I follow directly if you just make both of these equal to V. Anyhow. Okay. And that makes perfect sense in terms of what somebody just said. They were wanting to look at the projection of this vector on the x-axis, right? So you got this triangle. And A is the I component, so there's A. Is that clear? So this leg is A, and this is the length of the B vector, which is a square root of A squared plus B squared plus C squared, just by the Pythagorean theorem. But we're formalizing it in terms of dot product notation. And you want to do that. Okay, well then, your beta and gamma, very similarly, you're gonna have B over this thing. You're gonna have C over this thing. So you get these cosines, so you know what the angle is with each axis. If we're looking at a vector from here up to there, what angle does it make with the x-axis along that side of the room? Okay, well, there's a vector, there's the x-axis, looks like about 30 degrees or so. Okay, now according to this estimate, you can see, well, the estimate I used earlier, you can see if that makes about a 30-degree angle, okay? And with the y-axis and with the z-axis, with the z-axis, it's doesn't go up that much. Angle with the z-axis is probably around 15 degrees or so. Okay. Angle with the y-axis, well, there's a pretty big angle between there and the y-axis. So that angle might be 69.3 degrees. That's obvious. If you got a good eye. Okay. Okay, any questions on it? So this is all pretty simple stuff, especially if you've been where you guys have, having seen this stuff in linear algebra, and probably in pre-calculus, you're supposed to see this pre-calculus. And if you haven't, it's still pretty easy. Okay, somebody said it is A the length of this side of the triangle. And I said, yeah, and the way I explained it before, he said, I don't see it labeled. Well, I didn't want to clutter up the picture anymore. But it should be obvious that if B is AI plus BJ plus CK, that means you got A units here, that's AI, and then you add that to the BJ vector and to the CK vector to get this. So that side is clearly A. This side, well, this side is going to be square root of A squared plus B squared. Okay. And then sides are A and the square root of A squared plus B squared. You square those and add up and get this. If it's a right triangle, they work out. And it is a right triangle because that's a right angle there. It's projection. So make sure you understand everything I just said there. Just clarifies some of the ideas that I don't want to go into a lot of detail on because I think they're all fairly obvious. But the first time you're going through stuff, you miss stuff. Okay, so problems will, I think, be moderately challenging. Some of them just bonehead, straightforward, plug in, do it. Some of them get, I'd say moderately challenging. Okay, nothing excruciating. So you want to understand these basic ideas. Okay. Okay. V cross W is perpendicular. And to W. By the right-hand rule. Everybody know the right-hand rule? You just put your fingers in the direction of V, turn it toward W, and there's the direction of V cross W. If you do W cross V, you got to turn your hand like this, and it's going to be negative. Well, in the opposite direction of V cross W. So the right-hand rule tells you which direction it is. Magnitude of V cross W is the magnitude of V times the magnitude of W times the sine of the angle between them. So. By that definition, what's I cross I? Okay, so what's I cross I? Well, magnitude of I is I, magnitude of I is I, sine of the angle, well, the angle between I and I is zero, so the sine is zero. So the I cross I is zero. Well, I cross J. I'll just list these. Okay, I's in this direction, J's in this direction, K's in this direction, right? Put your fingers in the direction of I, turn them toward J, and your thumb points up, which is the direction of K. The magnitude is one because in all cases, we're just doing the different pairs of I, J, and K, turning them up in different ways. So the magnitudes are always going to be one. And if it's two different vectors, they're going to be at right angles. Because the X, Y, and Z directions are all at right angles with the others, each with right angles with each of the others. So, and I've got plus here instead of cross, that was a good thing. Okay, so I cross J has magnitude one. And by the right-hand rule, it's in the upward direction, which is the direction of the K vector. So I cross J is K. Okay, now what's I cross K? Now you want to think this through the way you can just list these. Okay, because it's very helpful in getting the right-hand rule straight before you have to use it in weird cases. Okay, the I is here and K is here, right? So if you put your fingers in the direction of I, turn them toward K, your thumb's going to go in the negative Y direction. That's negative J. That's negative J. And then we can kind of turn these around. J cross I is negative K because if you reverse the order of a cross product of a non-zero cross product, you're going to get a vector in the opposite direction. And you can do that also on J cross I. If here's J, you put your fingers in the direction of J, cross toward I, and your thumb points down. Okay, so you can do that both ways, and you should think that through. Think it through once a day until it's natural to you, because it'll save you time in the long run. And it's just really fundamental. If you're in any engineering that involves three dimensions and all of it does, you got to know this. I'll just state this, but you know, well, here's K, here's I, K cross I, J. Okay. And then you have let's do the cross product of J first. J cross J is zero because J is parallel to itself and the angle is zero. Okay. And J cross K, well, J cross K gives you I. And then of course, K cross J better be negative I. It's not something to memorize. You just got to know it by second nature. You should be able to visualize it instantly. If you got to use your hand, that's all right, you know. But you should be able to use your hand to do that. Now, if I missed any. Got J cross J, J cross K. I've got J cross I there, so I've got J cross with all three, right? And I've got K cross with I and K cross with J. And the only other one we could possibly do is K cross with K, which is obviously zero. Okay. So now What's this cross product? Now, you probably know how to write it as a determinant. And if not, I'm going to show you in a minute. It's easy, but it's quicker to do it using the distributive law if you've only got a couple of components in each vector. Okay? By the distributive law, this is equal to two I cross negative 5j plus 2I cross 2k plus 3k cross negative 5j plus 3k cross 2k. Make sense? And just like A plus B times C top plus D, going to be AC plus AD plus BC plus BD, right? Just a distributive law. Multiply this by this, this by this, this by this, this by this. Okay? Just like algebra 1. Okay, so this gives us negative 10. I cross J. Well, I cross J is K. I cross K. See, I cross K is negative J. K cross J. Well, K cross J is negative I. We have negative 15 times negative I plus 6 times 0. Okay. In other words, just factor out the numbers and do the cross product of the two unit vectors. Well, then it looks like we have 15I minus 4j minus 10k. That's pretty simple. And I recommend that you use the distributive law fairly often. But if you got three components, it's easier to write the determinant. Now, the distributive law will give you the determinant, and I think your book will tell you how that works. I'm not going to go into the detail because it's pretty simple. I mean, if you do like A1I plus B1J plus C1K cross with A2I plus B2J plus C2K and do it by the distributive law, you're going to get the same thing you get if you get a determinant. Now, to write the determinant for these vectors, I, J, I can start the first row with I, J, K. And then the second row will be the components of this vector. The I component's 2, J component's 0, the K component is 3. Makes sense so far? So you always start with I, J, K up here. You take the first vector and put it in the second row. Then you take the third vector and put its components in the third row. And span by minors. You've done that in linear algebra yet? Well, you will. Have you seen it before? Well, about time you saw it. I'm not going to explain it. Because you're going to get it. And your book will tell you it's easy enough. But well, I'll explain it briefly. All I do is I take this times the determinant I get if I eliminate this row and this, or this column and this row, which is this determinant. So it's I times the determinant that doesn't share a row or a column with I. Okay. Then the J, we throw J out. We throw the J column and row out, and we get Okay, but it's minus. Now, the rule is, and you'll see it in linear algebra, so I'm not gonna teach it to you in detail. You just take the row and column of I, which is row one, column one. 1 and 1 is 2. Negative 1 squared is 1. So we have a positive 1 times I. Okay. Now this is row 1, column 2. 1 and 2 is 3. Negative 1 to the third power is negative 1. So we have a negative sign there. Okay. Row 1, column 3. 1 and 3 is 4. Negative 1 to the fourth power is 1. So it's going to be plus k times the determinant, what we get if we wipe out the row and column of k. Now, there are other algorithms, like you can write 2, 0 out here and 0, negative 5 out here. And make lines and stuff. I don't particularly like that, but it's handy. So if you're going to calculate by hand, you can do that if you wish. But really it comes down to distributive law and determinant expansion by minors, because you can do this kind of expansion by minors for square matrix of any size. So that what we're doing here generalizes. If you had a 4 by 4 matrix, then you'd have 3 by 3 matrices down here. Okay. And each 3 by 3 would break down into 3 2 by 2s, and 2 by 2s are easy. Okay, well, the 2 by 2s, the determinant of a 2 by 2 matrix is the main diagonal, 0 times 2, minus the secondary diagonal, 3 times negative 5. Then it's minus j times 2 times 2, minus 3 times 0, plus k times 2 times negative 5, plus 0 times 0. And this comes out. Better come out the same thing as what I got. Negative 3 times negative 5 is 15, so there's 15i. So far, we agree with what the distributor law said. Screen's flashing, it's okay. And for the j, I get 4, but with the negative sign there, it's negative 4j. So we agree. Now, it's unusual that I do that much calculation and don't screw something up. So I must have screwed the last one up, but let's see. 2 times negative 5 is negative 10 on k, and yeah. Okay, well, just by dumb luck. The two methods agree. However you want to do the determinant, it'll work. If you do it right. Okay, here's a vector V, here's a vector W. These vectors define a parallelogram. Just draw a copy of V up here, and a copy of W up here. So here's another V, here's another W. What's the area of this parallelogram? How do you get the area of a parallelogram? Okay, so here's a parallelogram. Here's a vector V, here's a vector W. Draw a copy of V here, a copy of W here. You get a parallelogram. What's the area of a parallelogram? Area of a parallelogram. So let me draw one in standard, more or less standard orientation. Side is supposed to be horizontal. Okay, right there's a parallelogram, right? I can rearrange this parallelogram. I can cut off this triangle here. It's at a right angle. I can take this triangle and I can paste it over here. And now I've got a rectangle. Right? Okay, well then this distance here between the two sides is the altitude, which we often call h. And this side, which hasn't changed, is called the base. The area equals the base times the altitude. And you can deconstruct this into little rectangles of unit dimension and fractions thereof, and verify that the area has to be what it is. And if you don't know this, I don't see how you ever understand area of an integral in calculus. You don't really understand it if you don't know this. But it's okay to turn people, smart people like you guys, you're smart. It's obvious already. Okay, this is a smart group in a multivariable calculus course, okay? Nobody here should make less than a B, and y'all, if you put the work into it, I think you're gonna all make A's. Okay, and this is a tough course. But if you don't know these basic facts, you have nothing to build on. So while you're becoming top-notch engineers, while you're at it, just a side thing, reform all of the education in this country, would you please? So I don't have to put up with this every day. Okay. Well, by the time you reform it, I'll probably be doddering into my oatmeal. I'm already pretty much there. Okay, so anyhow, there we have it, right? I don't know how you dodder into your oatmeal anyway. Turns drooling into the oatmeal. Haven't started drooling, we'll see. Okay. You see what I'm talking about. You should know this very basically and should have been taught this starting in second grade. And probably were, and then got calculators put in your hands and didn't have to do it anymore, and didn't have to think about it. Solid formulas, but somehow you came out of it able to, so far, do really well in this course. So I'm kind of impressed. Okay, anyhow, this rectangle has equal area to the triangle, okay? To the parallelogram. I haven't made this terminology. I don't know these terms. What's the altitude of this parallelogram? Well, I have to extend this side to get the distance between the sides, which is measured at a right angle. Okay, that makes sense. Now, of course, I could have put this line here, again, at right angles, so we have a triangle here. Okay. Or I could have put it here. Now, actually, it makes this look kind of right angle. One way or another, I see this altitude as being equal to the length of this vector times the sine of theta. Now, if you like, you can put theta up here, that should be just automatic. Here's theta, here's the opposite side, here's hypotenuse. So I'm going to use V for the base, so here's the base. And here's the height. That's a magnitude of V cross W. We just defined it. Just learn how to calculate it. Okay. So that's an important geometric connection. And even better when it's a triple dot product, triple scalar product. Okay. So what I'm going to do is go into 3 dimensions. And let's just draw a vector V here. And a vector W out here somewhere. And a vector U, where U is in a plane different than the vectors than the plane of B and W. Okay. So what we have is, I don't have a parallelogram here. And we have an altitude well, not an altitude, but we've got the side here. We draw a W here, and we can draw a W here. I've drawn it very well, but and we can draw a W here, and we can connect these. And now we have a three-dimensional solid. Okay. Volume equals the area of the base times the altitude. And if you don't know this, you got it. Because we do vectors, integration in three dimensions, you got to have a picture for it. Okay, now we don't know exactly where these are. I haven't drawn the projections of the direction cosines or anything. But let's just say now that P cross W is here. Okay. Then the altitude, it's got to be measured as the distance between the base here and the base that we have up here. Okay, meaning it has to be measured perpendicular to the plane of B and W. Well, B cross W is perpendicular to the plane. And it follows that the altitude is just this. Okay. So one way to see it is the altitude is the projection of this vector on this vector. Okay. The area of the base is just the magnitude of V cross W, which is the length of this vector. So the volume equals this times H which is the projection of this vector on this vector. And now we haven't talked about projections. I need to do that before we're done. We've got time. Because that's the last thing I want to talk about. Okay. I'll use phi. Okay. Some people pronounce this phi, which I find offensive, because everybody knows the Greek alphabet. Phi, phi, pho, fum. Phi and phi are two different things, and this is phi, not phi. Got it? Now, if you mispronounce it, it's okay. A lot of mathematicians do. They're not the big mathematicians. Actually, the best mathematician in this area pronounces it phi. I've seen a lot of talks by him, given a few, and he asks really hard questions. So, good guy, really good guy. One of the best people around, but he pronounces it phi, so there's something wrong with his character, obviously. Okay. Well, it turns out that this is the same as U dot B cross W, isn't it? Now, what again? Let's be careful. Okay, I didn't label my because I got off the pronunciation. Okay. So you take the magnitude of this times the magnitude of this times the cosine of phi. That's what you got here, right? But that's just the dot product of this vector and this vector. Once you understand dot product better, it'll be obvious. Okay, that's an important picture. Your book, I think, has. I don't know how anybody could draw a better picture than I did, but I think they did. Okay. Okay, now I neglected the mention projections. Oh, here we go. This is really important too. This vector is the projection onto W of vector V. The projection V onto W, just like you project a point in the plane on the x-axis or the y-axis, or point space on the x and the y and the z-axis, okay, to get your components. Very same thing. Okay. Now, what's the formula for the projection of V on W? First of all, the length of this vector. Let's put W there. The magnitude of this projection is just what? Well, okay, right there's again, V dot W is product of these magnitudes, right? The magnitude of the projection is just magnitude of V times cosine theta, right? Now, what do you have to do up here to get the magnitude of V cosine theta? Take the right-hand side. What do you have to do to the right-hand side to get magnitude of V cosine theta? You have to divide by magnitude of V. I'll be explicit about this just because it's getting a little late in class. Might be getting a little bit less alert. Although, even if I don't necessarily expect that, it's this, obviously, right? And it's very not blue. Okay. But of course, this numerator is just a dot product, so it's V dot W over the magnitude of W. Which of course is the same. Well, that the projection is in the direction of W. That's a multiple of W over the magnitude of W. Now, what do you call W over the magnitude of W? What kind of a vector is that? You might or might not know. Expected I got a quick answer. It's a unit vector. You divide a vector by its length. If a vector is 10 units long, you divide it by 10, it's 1 unit long. Or you get a vector that's 1 unit long. Okay. This is a unit vector in the direction of W. So the upshot of all this is this vector equals the magnitude, the length of this vector multiplied by the unit vector gives you a vector in the direction of W and its length has to be equal to this side of the triangle. Now, the projection might be in the opposite direction. This vector might be this way. Your projection might be a negative multiple of W over magnitude of W, but it's going to come out of this calculation. Now, one thing that texts always do, and they just won't listen to me. It makes no sense for me to obscure the fact that you're multiplying something you get from a triangle, which is this, by a unit vector, which tells you geometrically what's going on with a projection. They always want to just make this V dot W over magnitude of W squared times the W vector, obscuring the fact that you're multiplying something that's just a side of a triangle, the length of the side of a triangle, by a unit vector. Okay? So people use that formula without understanding that. And then later on, maybe in a different course, maybe on a final exam, they forget the formula and don't know where it comes from. And it's very simple where it comes from. I advocate you understand this and don't use that stupid formula. This is almost as easy to write down. How much longer does it take to write a magnitude of W here than it does to put a square on this? A little longer, 3 seconds, okay? Use the 3 seconds and do the thing in the sensible, doggone way. And anybody that wants to argue with me on that, I'm ready for you. Not you, you don't get to argue with me, really. I'm talking about people out there who really think that that formula is more important than this picture. Okay, come on, I'm ready for it. Well, I'm not ready for much of anything physically, but you know how it is. Okay, but I'll argue you into the ground on it, though. It's stupid. And it's just there because people used to think you just teach people formulas and then they understand everything. That's true if the people are smart enough. They learn what the formulas mean and why they are and stuff like that. But it's easier to learn it if you know what's going on. Okay, know where it comes from, especially when it's as simple as this. Now, this is all actually pretty simple. So you want to look at it and think about it until you find that it really is simple. See, I'm not ready to even hang with anybody. I can't even walk straight. Okay, make sense?
Yep.
Have a good time. We'll go on with this Thursday, but do get into the homework.